everyone. I welcome you all to our new online lecture series on process measurement and instrumentation. This is an undergraduate lecture series aimed at chemical and process engineering curriculum. However, the subject matters that we discuss here are useful to any engineering or technical professional engaged in the process industry. This lecture series covers temperature measurement and instrumentation, solved examples on temperature measurement, pressure measurement and instrumentation, level measurement and instrumentation, flow measurement and instrumentation, summary of other instrumentation, analytical instrumentation, and piping and instrumentation diagrams. So in this first lecture, we are discussing about temperature measurement and instrumentation. First of all, let's discuss about what is temperature. We all know that the temperature is a parameter that we use to determine the sensation of warmth or coldness. In addition, a temperature can be used as a measure of the average kinetic energy of a certain molecules or particles in a sample of matter. I hope you have learnt about the basic thermodynamic laws. Those are related to temperature and the behavior of matter under different temperatures. So based on that, we know that if two bodies at the same temperature are connected together, the joint body has the same temperature as each of the original bodies. This relates to the zeroth law of thermodynamics. As well, in the absence of absolute standard in the form of a relationship between measurable quantities, it is necessary to establish fixed reproducible reference points for temperature. The International Practical Temperature Scale uses this philosophy and has defined 6 primary fixed points for reference temperature in terms of the triple point of equilibrium hydrogen, that is a minus 259.34 degrees Celsius, the boiling point of oxygen, that is minus 182.962 degrees Celsius, the boiling point of water, that is 100 degrees Celsius. The fourth fixed point is the freezing point of zinc, that is 419.58 degrees Celsius. And the fifth one is the freezing point of silver, that is 961.93. And the last primary fixed point is the freezing point of gold, that is 1064.43 degrees Celsius. All these fixed points are at standard atmospheric pressure. In addition, the freezing points of certain other metals can also be used as secondary fixed points to provide additional reference points during the calibration procedures of temperature. We all know that there are several units to indicate the temperature. They are Fahrenheit, Celsius, Kelvin, and Rankine. So this slide gives you some information about the temperature scales available and the conversion formula between each units. I'm not going to discuss in detail about this because this is fundamental knowledge, and even you have learned this in secondary school as well as advanced level syllabus. So we are moving to the next slide. And this slide further describes you the relationship between the different units of temperature, starting from the absolute zero, how the four temperature units have their relationships to each other for conversion. I'm just reviewing this part because the knowledge on temperature units is also important when you discuss about temperature measurement and instrumentation. Let's further discuss a few more general knowledge on this. We know that in our practical life and scientific applications, how temperature varies. The range of temperatures available in this world are starting from nearly absolute zero to thousands of degrees Celsius temperature. For examples, we can start from the lowest temperature, something like cosmic background radiation, that is around minus 270 degrees Celsius. And then we can go a little further, cryogenic storage of liquid nitrogen, that is around minus 196 degrees Celsius. Then all the time the coldest point on the earth might be in Antarctica or somewhere, is minus 89.2 degrees Celsius. Then we all know that the freezing point of pure water, that is around 0 degrees Celsius. Then boiling point of water at 1 atmosphere of pressure, that is around 100 degrees Celsius. Then the melting point of gold, that is around 1064 degrees Celsius. Then we can go further in the scale of 1000 degrees Celsius. 1200 to 1500 degrees Celsius would be the molten glass steel temperature. And then the temperature of the surface of the sun is around 6000, while the temperature of the center of the sun is around 15 million degrees Celsius. So that means we have to cover a huge range of temperature, and most probably in process industries, of course, we don't have to cover up to millions of degrees Celsius, but from our temperature measurement instruments, we have to cover around certain minus degrees Celsius to certain thousands of degrees Celsius. So this would be the range that we are focusing on temperature measurement and instrumentation. Starting on different temperature measurement instruments, in this lecture, we are going to discuss several physical principles that we use, otherwise the principles behind the development of a temperature measurement instruments. Why? Because learning the physical principle, operating principle, or the theory behind developing the measurement instrument is very important for the understanding of the process engineer's job in the process industry. So under the physical principles for temperature measurement instrumentation development, we are going to talk about thermoelectric effect, a thermal expansion, resistance change or radiative heat emission, then some advanced principles like thermography, color change, sensitivity of semiconductor device, resonant frequency change, sensitivity of fiber optic devices. So there are many such principles. Those are used to develop temperature measurement instruments. However, due to the limitation of time and more focus on widely used instruments, here we are going to talk mainly from thermoelectric effect to radiative heat transmission. So most probably we would be talking about thermocouples, resistance-based temperature detectors, thermistors, and semiconductor-based ones, as well as radiative thermometers. Talking about thermoelectric effect, that is the theory behind the thermocouples. The discovery was made by J. Seidbeck in somewhere around 1821. He discovered that when any two different metals are connected together, an electromotive force is generated at the junction between the metals. So this is the principle behind a thermocouple. As shown in the figure, there is a junction. You can see there is one metal strip in red color and the other one is in blue color, and an electromotive force is generated at the junction that can be observed by a voltmeter or an ammeter. From the basics of electricity, we know that metals are good heat conductors as well as electrical conductors. So when heat flowing in a metal, it produces a movement of electrons, and therefore an electromotive force is generated. So this electromotive force is a function of the temperature difference between the joint and the voltmeter connection. So as you can see, there's an equation provided. It's a power series of temperature. That would be the equation for the electromotive force. For certain pairs of metals, we can neglect the higher order terms of temperature in this equation. One example would be iron and constantan. So if we use iron and constantan thermocouple junction, we can represent the relationship between the electromotive force at the junction and the temperature at that junction is a linear equation. That is simply electromotive force is equal to a coefficient multiplied by the temperature. Something like E is equal to A1T. As I explained you previously, if there are two junctions, we can see that a current will flow through the circuit. Of course, if there is an electromotive force, there would be an electrical current flows through that junction. This electrical current is also proportional to the temperature difference between the two junctions. As shown in this figure, there are two thermoelement materials or metals, and there are two junctions. So one junction can be kept at a known temperature and the other junction can be kept at the unknown temperature. Then we can calibrate the electromotive force or the electrical current, and based on that we can find the unknown temperature. So that is the methodology of finding out the unknown temperature using thermocouples. Here we can see certain thermocouple materials. Those can be used in the linear scale for the relationship between temperature and the electromotive force. In standard coding, the type of these thermocouples are named as E, J, T, K, R, S, like that. If we take the type E, that is chromal constantan junction, and type J is iron constantan. So like that, type T is copper constantan. Like that, there can be several thermocouple materials. In this graph, we can see how individual thermocouple material or the metal junctions behave in the scale of temperature with respect to the electromotive force. So we can see that some thermocouple materials can be used for a wide range of temperature, while some are having a narrow range of temperature. An example would be the type E, that is chromal constant thermocouple, that has a lower temperature measurement range compared to the type J, that is iron constant. So like that. So the coefficient A1 in that equation is when it is larger, the temperature range that can be measured is reduced. When we measure the temperature using thermocouples, we have to consider several laws of thermocouples. Basically, there are 4 thermocouple laws. By names, we can define them like the law of interior temperatures, the law of inserted materials, the law of intermediate materials, and the law of intermediate temperatures. So there are 4 thermocouple laws. The first law, that is the law of interior temperatures. That means, as you can see in the picture, the electromotive force of a thermocouple with the junction at T1 temperature and terminus connection at T0 is unaffected by the temperature elsewhere in the circuit, provided the properties of the 2 thermo elements used are homogeneous. So this means here we have 2 thermo elements in a thermocouple, thermo element A and thermo element B. So if they are having homogeneous properties, the electromotive force is unaffected by the temperature elsewhere. So here we have T0 temperature, and at the junction we have T1 temperature. So they are independent. They are not affected by the hotspot temperature available in somewhere. So the second law, what does it say? The law of inserted materials. That means if a third homogeneous material, that is called as material C, is inserted to either thermo element A or thermo element B, then there will be 3 junctions actually. So as long as the 2 new thermoelectric junctions are at the same temperature, the net electromotive force of the circuit is unchanged irrespective of the temperature in material C, which is away from the thermoelectric junctions. So this is very important, that sometimes we can neglect disturbance temperature on the measurement system using the thermocouple laws. Then the third law, that is the law of intermediate materials. Insertion of an intermediate metal into a thermocouple circuit will not affect the net electromotive force. So here, as you can see in the picture, there is an introduction of thermo element C in between thermo element A and B. So there are 2 junctions created, but these 2 junctions are at identical temperature, T1. So it does not affect the net electromotive force. So this is very important when we talk about the application of thermocouple. Then the fourth law of thermocouples is the law of intermediate temperatures. That means if a thermocouple circuit develops an electromotive force E1 with its junctions are at T1 and T2 temperatures, and another electromotive force E2 with T2 and T3 temperatures at the junction, then the thermocouple will develop an electromotive force that is equivalent to E1 plus E2 with its junction maintained at T1 and T3. So insertion of a third temperature called T2 will not affect, and we can use these laws to measure the temperature detected from thermocouples. Then we discussed that when using thermocouples for temperature measurement, there should be a reference junction. The reference junction would be an ice bath that can be named as cold junction. The actual voltage produced by the junction that is measuring the amount of temperature can determine the temperature accurately. And normally we have to compensate the reference for the measurement. That is called cold junction compensation circuit. As you can see in this picture, cold junction compensation circuit provides the equivalent voltage produced by the junction in an ice bath or other reference junction, so that the actual voltage produced by the junction that is measuring the amount of temperature can determine the temperature accurately. Using the compensation circuit, we can reach the actual temperature based on the reference temperature. As you can see in this figure, there's ice water bath at T1 and the unknown temperature is T2. So based on this reference temperature, we can find out the unknown temperature. Another example would be we can use a known reference junction temperature in addition to ice water bath. The second type of temperature measurement devices that we discuss in this lecture is thermal expansion devices. Under this, we can categorize liquid in glass thermometers, bimetallic thermometers, and pressure thermometers, which use the thermal expansion principle to measure the temperature. First, the liquid in glass thermometers. We all know that the household thermometers as well as the laboratory thermometers that we use are mainly liquid in glass thermometers. Normally we use mercury or a similar heat conductive fluid with a bulb and a capillary tube. So you can see in the figure in the slide, there is a bulb and a capillary tube with the scale, and accordingly when we place the bulb at the unknown temperature, the fluid expands and it shows the temperature measurement because the expansion of the fluid is directly proportional to the temperature change or the temperature that we don't know. The range of these liquid in glass thermometers can vary from minus 200 degrees to 1000 degrees Celsius, quite a large scale. A practical scale of temperature is covered. The process of estimating the position of the curved meniscus of the fluid against the scale introduces some error into the measurement process. So liquid in glass thermometers would have a certain error, and the accuracy is a little lower compared to thermocouples or other temperature measurement devices. Then we can focus on bimetallic thermometers. In bimetallic thermometers, we use two strips of different metals that are bonded together. We know that the metals expands when the temperature is changed. So when there is a bimetallic strip, what happens is, because it can't expand together, there is a bending happens on the bimetallic strip. So this action can be used to measure the temperature, the magnitude of bending can be arranged to a temperature scale with the proportionality between the magnitude of bending and the temperature. So we can obtain the temperature scale or indicator using bimetallic strips. Even these bimetallic strips can be arranged in spiral or helical configurations also. This figure shows you a bimetallic thermometer. As the temperature changes, the helical element coils or uncoils. The turning of the helical bimetal element turns the pointer. So then we can know the temperature accordingly. So the inaccuracy of the best bimetallic thermometers can be as low as 0.5%. This is better than the liquid in glass thermometers. As well, there is a quite practical temperature range, but sometimes the highly accurate devices are a little expensive. Then the third type of expansion-based thermometers is the pressure thermometers. That depends on the relationship between volume and pressure. We all know that based on the Boyle's law, for a certain temperature, the relationship between volume and pressure is a constant. So using this, a sensing element in the pressure thermometer is a certain bulb. It's a stainless steel bulb containing a liquid or a vapor or a gas. When the temperature changes, what happens? The fluid is not constrained in the bulb, then the volume changes. If the temperature increases, the volume also increases. Then we can use the change of volume as a measure of temperature, or otherwise we can constrain the fluid in the bulb. Then volume is constant. Then with the change of the temperature, pressure changes. So either way, we can obtain a temperature scale proportionate to the pressure change or the volume change, and accordingly we can have the temperature indicator or the thermometer based on the concept or the pressure thermometer concept. So as you can see in this figure clearly, a hollow spiral metal tube is used. Inside the bulb, it might be a volatile liquid, a gas, or a vapor. So when the temperature changes, this gas or the liquid or the vapor expands. Due to the expansion, this tube is unwinded. That creates a movement in the indicator. So we can scale the indicator with the proportionate temperature scale. This principle can be used to one specific device that is not only used in temperature measurement as well as it is used in pressure measurement, that is called Bourdon tube. So Bourdon tube, the concept is the same, where the bulb is there, and due to the liquid expansion that changes the temperature is the principle behind the Bourdon tube. Bourdon tube gauge is one of the most commonly used temperature measurement device in the industry. So in addition, we can use gas-filled thermometers using the same principle. That is a very simple and unpowered device with great reliability and repeatability. Or sometimes gas-filled thermometers are very useful in the industrial applications where it is difficult to use a liquid inside for the thermal expansion devices. Changes in ambient temperature along the capillary or the scale do not affect the thermometer readout. This means that capillary up to 75 feet long can be used without the need for ambient temperature compensation. The range that can be covered by these pressure thermometers would be around minus 250 to 2000, quite practical temperature scale with great accuracy level. One of the disadvantage of pressure thermometers is sometimes the response time is a little longer than the other types of temperature measurement. The next important type of thermometers is the resistance thermometers. We know that the resistance of a metal also varies with temperature according to the relationship between temperature and the resistance change. So that is a linear relationship because normally we can write an equation between the initial resistance and the resistance after the temperature change is a power series, but we can neglect the higher order temperature terms for a certain materials. Then we can have a simply linear relationship between the two resistances that has a linear relationship to the temperature. So we can use certain metals like nickel, copper, platinum, tungsten. They can be the elements in the resistance temperature devices because their linear resistance temperature relationship, and they have a high coefficient of resistance and their ability to withstand repeated temperature cycles. In this slide, it explains about the internal construction of a resistance thermometer. So normally these metals are, an example would be platinum wires. They are placed like spring-like wires surrounded by an insulator material. So sometimes it's enclosed in a sheath of metal. Then in this type of thermometers, there is a protective well and a terminal head, right? Why we have this protective well and a terminal head? Because a well is required to protect the resistance thermometer from damage by the gas or liquid being measured. Then the protecting wells are normally made of stainless steel, carbon steel or cast iron, and they are used for temperatures up to 1100 degrees Celsius. Sometimes resistance-based temperature devices can be used in a Wheatstone bridge circuit where three resistors, three known resistors and the unknown resistance that corresponds to the unknown temperature with a voltmeter, and the voltage source is used as shown in the figure. From the Wheatstone bridge circuit, we can find out the unknown resistance that corresponds to the unknown temperature. So accordingly, we can with the Wheatstone bridge circuit scale that corresponds to the moving coil millivoltmeter can be scaled with the temperature proportionate to the unknown resistance in the Wheatstone bridge circuit. So there is also another way to fix a thermometer based on resistance change. Then another important type of temperature measurement devices is thermistors. Thermistors are also resistance based temperature device. In thermistors, by passing a current through it, the voltage across the thermistor is read and the temperature can be determined. So the thermistors also have a higher sensitivity and higher resistance also is there. So it can be used well for temperature measurement. A thermistor is made of a mixture of semiconductor powder compounds such as nickel oxide, manganese oxides, and cobalt oxide. The thermistors are shaped as cylinders, discs, beads, or sometimes rods. The material is compressed, sintered at high temperature, connected by two leads, and insulated. So as shown in these figures, there are several types of thermistors such as bead, coated bead or rod, and chip type, as well as rod with glass tip. Like that, there are several shapes of thermistors available. Normally a bead type thermistor, the construction of this thermistor is shown in this slide. We can see the different sections of this small thermistor device. If we talk about the relationship between the resistance in the thermistor and the temperature, actually thermistors have a negative temperature coefficient, where it is little different from the other resistance and temperature relationship. However, we can use this relationship as shown in the equation. We can use it for a certain range. We can use it to measure the temperature. As discussed previously, similar to the Wheatstone bridge circuit, the thermistors also can be used in bridge circuits and find out the unknown resistance with respect to the unknown temperature. The last type of temperature measurement devices that we discuss in this lecture is radiative emission devices. Under that, we discuss at first one important temperature measurement devices, that is pyrometers. We can have several types of pyrometers. In general, also we can call all the radiation thermometers as pyrometers. But later we can divide them into three important types. So all objects, we know that all objects emit thermal radiation. The amount of radiation emitted by each body can be measured and related to the temperature using the Planck law of radiation. I hope that you have learned the Planck law of radiation. So the temperatures can be measured remotely using this technique. That is the most important thing why the pyrometers are very famous in temperature measurement. We can develop the sensing ability, temperature sensing ability, as well as the temperature controlling devices using this remote measurement advantage. Most importantly, for very hot, moving or hazardous environments, this technique is very useful to measure the temperature. So nowadays we know that the entire world is facing a huge crisis due to COVID-19 outbreak. We have seen this picture actually, this measurement of body temperature of people to identify the patients, COVID-19 patients having fever in their body. So when they enter to a country through an airport or any clinic or something, or any quarantine activities or something, we can check the body temperature in a remote base without getting the infection from the patient to the healthcare professionals. Easily the body temperatures can be measured and recorded using the infrared thermometer. That is one type of pyrometer. So the principle of this infrared thermometers is Actually, in any infrared thermometer, there is infrared transmitter and infrared receiver. So when you want to measure the temperature, you have to send a transmitted infrared signal to the object, and the reflected infrared is received, and based on that an electronic circuit is used inside to display the digital temperature measurement. So further discussion on pyrometers. The types of pyrometers, as I told you previously, there are three main types. One is total radiation pyrometers, number two is optical pyrometers, and number three is infrared pyrometers. Total radiation pyrometry principle is the radiation detector is a thermal detector which measures the temperature rise in a black body at the focal point of the optical system. So in total radiation pyrometry, there is a focusing lens and a detector is used. So the radiation signal is focused on the detector and measured. In optical pyrometry or optical pyrometer, it is designed to measure the temperatures where the peak radiation emission is in the red part of the visible spectrum. So there are several lenses used in an optical pyrometer. Based on this focusing of the radiation, the incoming radiation is focused, and it can be converted to temperature measurement. Then the infrared pyrometry, as I described previously, the infrared instrument employs a photocell to detect the photon flux. So that is what I discuss as the infrared transmitter and the receiver. And or otherwise we can use a photon detector or a photocell. So using that we can identify the unknown temperature. So according to the Planck's law of radiation, the radiation varies as the fourth power of the temperature of a certain body. In addition to the radiation pyrometers, we can use semiconductor devices where a semiconductor bar is used. When detecting the emitted radiation from a body, thermal detectors and direct quantum detectors are used. In thermal detectors, the radiation signals received are converted to heat, and accordingly the temperature can be measured. In direct quantum detectors, the photons in the radiation can convert directly into electronic signals in a semiconducting bar. Then based on the electronic signal, the temperature can be measured. So in this lecture, we discussed the operating principles of several thermometers or temperature measurement devices. Under that, we mainly discussed the thermocouples based on thermoelectric effect and thermal expansion devices like liquid in glass and bimetallic and pressure thermometers based on the thermal expansion principle, and the resistance change principle can be used for temperature measuring devices, including the thermistor, and lastly the radiative heat emission based thermometers like radiation thermometer or like the infrared thermometer and other pyrometers. So here is the reference textbook for this lecture series, that is the Measurement and Instrumentation Principles, written by Alan S. Morris. There is the third edition of Butterworth-Hyman publications. So you can refer this reference book for further self-study and knowledge on other temperature measurement principles like thermography, color change, sensitivity of semiconductor devices, resonant frequency change, sensitivity of fiber-optic devices, like that. So as final remarks, I would like to discuss one more important thing, that is on how to select the temperature instrumentation in process industry. That is the application part of this knowledge, because why we learn all these theories is to apply as engineers in the industry. If we talk about the applications, base metal thermocouples are relatively cheap. There is a certain practical temperature range that can be measured by thermocouples. So based on the application, we can select thermocouples for our temperature measurement requirement in the industry. Then the other thing is, sometimes thermocouples having noble metals are required because they are chemically inert, and for corrosive environments and specific requirements, specific applications, we would be in need to use these special type of thermocouples, which are a little expensive. The other thing is, in overall, all types of thermocouples have a low level output voltage that makes background noise or something to the measurement, some disturbances to the measurement. Therefore, sometimes for certain applications where we need to measure very small temperature differences, thermocouple would not be suitable in that case. That is where we have to use other types of thermometers, like resistance thermometers. They are also in common use in the industry. They have a smaller temperature range than thermocouples. Even though they have a smaller temperature range than thermocouples, they are more stable and even can measure small temperature differences. The other thing is, the range of instruments working on the thermal expansion principle are mainly used as temperature indicating devices rather than the automatic control systems, because we have to discuss about control systems also. Process industry, normally we have to control these parameters like temperature, pressure and all. So when we have to control the temperature of a certain process or a certain unit operation, we can couple the measurement device with the control circuit. But when we use these thermal expansion principle based thermometers like liquid in glass thermometer or something, they are just indicators rather than controllable devices. Then lastly, thermistors are small and cheap with very low cost, but they give a fast output response for temperature changes, and good measurement sensitivity is there with thermistors, because nowadays thermistors are also one popular mode of temperature measurement. So I hope that in this online lecture you learned about different types of temperature measurement devices in the process industry. I hope you can use this knowledge in the process industry one day when you have to order a new instrumentation for your process to measure the temperature, especially when you have to design a new plant or for when you launch a new process to a new product or something like that. So those are the applications. So I hope it was really useful for you. So we will meet with another lecture like this. Until we meet again, have a nice day and goodbye.